Okay, so 3.4 is going to look at linear and angular speed. Okay, so looking at this picture right here. So linear speed, just if you have a circle and you're to put a point on the edge and trace it, the linear speed is just that distance over time, and that's what you see right here with this formula. So we typically use V to indicate linear speed, so it's arc length divided by time, so distance over time. And same thing for our angular speed right here. So if you're looking for an angle, so if you're rotating this around the circle, the angle that is created over a certain amount of time, that's how you could figure out your angular speed. So how much of an angle have you rotated over a certain period of time, and that ratio will give you your angular speed. And so going down here, it would seem that there would be some type of connection between linear speed and angular speed, and that is true. So if you look here, here's our angular speed, here's our linear speed. And so remember, linear speed actually has arc length, which has its own formula. So arc length is actually equivalent to radius times theta, right? Your angle of rotation theta. And then what you could do here is you could kind of break this apart and put it as r times theta over time, which is actually the same thing as our angular speed right here. So you could substitute that for angular speed to where arc length is actually equivalent to radius times angular speed. And so anyways, that might be helpful as we kind of work through some problems here. Okay, but what we're going to do is we're going to start out just working with these three formulas right here: angular speed, linear speed, and then the one where we manipulated it. We're just going to kind of basically do some algebra here. It shouldn't be anything too difficult. So on our first example right here, we have angular speed is equal to theta divided by time. Solve for the missing variable. So on this first one, we're missing the angle right here, theta. So what we'll do is we'll fill in everything we know and then solve for what we don't know. And like I said, these should be fairly basic. So here we'll multiply both sides by 3 to solve for theta. And so that cancels, so we're left with 2 pi equals theta. So theta is equal to 2 pi radians. Okay, on this next one, it actually looks pretty much the same, except we're dealing with decimals. So we have 0.91 for W, for our angular speed. And then, let's see, that's equal to theta over 8.1. And so what we'll do is we'll multiply both sides by 8.1. And let's see. And then when we do that, you can see it on my calculator, you're going to get 7.371. And that would be, let's see, we're talking about theta, right? So theta is equal to that, and that will be radians. Okay, for our next one, they actually give us the angle and they give us time. We actually are solving for angular speed. So W equals, and so it's going to be 3 pi over 4 divided by 8. Okay, so once again, just a little algebra here. So what I'm going to do is I'm going to turn that 8 into 8 over 1. That's the same thing. So now I have a fraction divided by a fraction. So we're going to do this little thing called KFC, where we're going to keep the first one, and then F is going to be KCF, I'm sorry, KCF. Then we're going to change the division to multiplication, and then we're going to flip the last one to 1 over 8. So keep, change it to multiplication, then flip it. All right, so then we go ahead and just multiply across, and we're going to get 3 pi over 32, and that will be, let's see, that is our angular speed. So that's going to be radians per second right there. So that's how fast we're going. That's how many radians the angle is rotating every second right there. All right, got some more here. Oops. Here we go. Here's our next example. So now we're looking at using this formula for linear speed, which is equal to radius times angular speed. So once again, we'll just solve for the unknown. So in this particular case, it's going to be the linear speed. So V equals 12 times 2 pi over 3. And this shouldn't be too bad. We're just going to reduce this a little bit. So the 12 and the 3 can reduce to a 1 and a 4. And then we'll multiply that together to get 8 pi. So we're talking about linear speed. So we're talking about a distance over a certain amount of time. So we're talking about meters per second. There we go. Okay, part B, it looks like, let's see, we're missing the angular speed on this one. Okay, so we'll go ahead and solve for that. So let's see, we know 9 equals 5 times W. So then we'll divide both sides by 5. And so that's what our angular speed is going to be here. So we're going 9/5. Looks like we're going to be doing radians, and then it's going to be per second. Okay, so the angular speed will always be radians, and then I had to just figure out, are we doing minutes, seconds, or whatever. And so in this case, it was seconds. Okay, so now the fun part, we're going to get to some word problems. So right here it says, find the linear speed V for each of the following. So the tip of a minute hand of a clock, if the hand is 7 centimeters long. Okay, and I believe on your homework it's going to ask you for the speed per minute. And yes, okay, I just double checked it. So yes, it's going to be per minute. So here's the hand, 7 centimeters long, okay? And so we want to figure out that linear speed. Okay, so really what we're going to do here is you're really just figuring out the small arc length right here because it's going to be per minute. So really what we're going to do here is you're really looking for arc length. So if remember, arc length is going to be radius times theta. And so we know the radius is 7. We have to figure out the theta part, and we need to do it in radians. So, you know, there's 60 minutes in an hour. So basically, it's going to be 1/60th of a rotation is what's going on. So a full rotation would be 2 pi. So theta is going to be 2 pi divided by 60 because we're only doing 1 minute. So we're going to break that up. So 2 pi would be a full rotation. So we're going to do 1/60th of that. So we'll go ahead and simplify this. And so let's see, that'll become pi over 30. So that's going to be our theta for our arc length here. So we'll go ahead and solve this. So this will be 7 times pi over 30. So we're getting 7 pi over 30. So that's going to be your arc length in centimeters. That's how far you're traveling, right? And so our linear speed is going to be our arc length divided by time. So we're going to have 7 pi over 30, and then we're only going 1 minute, so that's our time right there. So it's kind of silly. So it's just going to be 7 pi over 30, and that's going to be centimeters per minute. Okay, our next one. So it says the tip of a propeller, 3 meters long, rotates 500 times per minute. And so it says, hint, basically they're going to tell you the radius is 1.5 meters. So the tip of the propeller, 3 meters long, rotates 500 times per minute. Okay, so we want to figure out that linear speed per minute. Okay, so if we're going to rotate 500 times. So once again, let's see. So we're looking for theta divided by time. And so if we're going to do it 500 times, that means that our angle theta, if it's rotating that many times, let's write this down. So one rotation would be 2 pi. So if you're going to do it 500 times, you got to multiply that by 500. So theta in this case is going to be 1,000 pi, okay? And then time in this case is going to be, oh, I'm sorry, I wrote down the wrong, that should be arc length, sorry. But we're still going to need all this information anyways to figure out arc length. Okay, so now that we have that, then we can multiply that by the radius to figure that part out. And then we'll go ahead and divide by time and we'll figure this all out. Okay, so here we go. So now we'll figure out our arc length, which is radius times theta. And so let's see, our radius is 1.5. Then we're going to multiply that by our angle of rotation here. So 1,000 pi. And so that's going to be 1,500 pi. And that would be, let's see, we're talking about meters here. Okay. And then time is just 1 minute. So just like the previous one, we're just going to divide by 1. So it's kind of not really going to change anything. So you divide by 1. So our linear speed is 1,500 pi. And then that's going to be meters per minute. So that's how fast that point on the edge of the propeller is going. So that's the linear speed. Okay. All right, our next example down here. So the speed of a pulley in a belt. The pulley shown has a radius of 12.96. Suppose that it takes 18 seconds for 56 centimeters of belt to go around the pulley. So 18 seconds for 56 centimeters to go around the belt. Basically, they're telling you the arc length over that amount of time right there. Okay, so right here it says find the linear speed of the belt in centimeters per second. Okay, so if we go back to our linear speed, that's going to be arc length over time. And so, like I said, 56, that would be the arc length, and then the time would be the 18 seconds. So that's going to be pretty simple to get right there. So we've traveled 56 centimeters. That's how much the belt has gone around this in an 18-second period of time. So then we'll divide that by 18, and then we'll want to go ahead and reduce that. So let's see, cut that, let me see. Looks like they're both just going to be divisible by 2. So let's see, that'll be 28 over 9. And then let's see, what are we talking about here? Linear speed. So we're talking about centimeters per second. So that's our first part. So then we're going to find the angular speed of the pulley in radians per second. All right, so angular speed is going to be our angle of rotation divided by time. Now, this is where some of those other formulas might come in handy. So if you remember, the other formula for linear speed was radius times angular speed. Okay, so remember when we manipulated that, that was on the very first page. So what I could do here to help me here is I could just divide by r, and that would solve for angular, my angular speed right here. So I already have those pieces of information right here. I have the linear speed, which is 28 over 9. And then I just have to divide by the radius, which is 12.96, okay? And then we'll just go ahead and put this in your calculator. And looking at the homework, it's going to ask you for a decimal anyways. So let's see, 28 divided by 9, and then We'll divide that by 12.96. And, oops. Let's see, and that will give us 0.24. And that's how it will be on your homework. You'll just do a couple decimal places. So it's going to be 0.24 radians per second. Okay. All right. I think I have just a few more examples of this. Okay, so right here it says the radius of a spool of thread. The thread is being pulled off the spool at a rate of 59.4 centimeters per second. Find the radius of the spool if it makes 152 revolutions per minute. So let's look at what's given here. So they give us, basically they're giving you the arc length per second. Okay, so they give you the arc length, or well, linear speed per second, but same thing as arc length for 1 second. So the arc length is going to be equal to 59.4. And so if you remember, arc length is radius times theta, right? So what we can figure out here is they tell us that there's 152 revolutions per minute, right? So if we divide that by 60, it'd be 152 over 60. That'd be revolutions per second, right? So now I have the revolutions per second. I have the arc length for 1 second, right? So what I can do here is I need to plug this in for theta, but I have to convert it to radians. Right now it's in revolutions. So each revolution is equivalent to, so 1 revolution is equivalent to 2 pi radians. So what we're going to do here is multiply this by 2 pi. Okay, so that's going to give me 304 pi over 60, or I guess I could reduce that actually. We'll just go ahead and reduce that now. So I can reduce the 60 and the 2. So we're going to have 152 pi, which, yeah, I can reduce further. And we can do that in a minute. And so that's going to be radians. It's going to be radians per second. So we converted from revolutions to radians. Now you can reduce this more or not. It doesn't really matter because we're going to have to use the calculator to plug this in anyways. And so coming down here, so I've got 59.4 is equal to my radius times 152 pi over 30. Okay. Now, we want to solve for radius, so we just are going to divide both sides by this. So you're going to have to be careful depending on what calculator you're going to use to input this, because it can be a little tricky. So we're going to divide over here by 152 pi over 30. Now, if you're using a graphing calculator similar to this one, so it should be fine. You can just put it in the way you see it. You just gotta make sure you put in your parentheses. So 59.4 divided by, and then you're gonna want to open a parentheses just to be safe. So 152 pi divided by 3. And I'll close that, and that should work for us. So let's see, 0.373. I don't know what I was thinking. I missed a 0 right there, so let me fix that. So second, and oops, let's see, second, enter, there we go. So I'm sorry, that should be 30 right there. Okay, so now we'll try that. Okay, there we go, 3.73, that's much better. So 3.73, and that'll be centimeters, and so that would be the radius right there. Okay, so once again, they gave me an arc length for a period of time, and then the arc length is radius times theta. They told me how many revolutions per minute, so I had to do some conversions to convert it to seconds per second, since the arc length was given in seconds, and then I had to convert the revolutions to radians. Okay, and then plug it in here, and works out. The algebra shouldn't be too difficult. It's just getting the setup going. Okay, our last one right here. So angular speed of a motor propeller. The propeller of a 90 horsepower outboard motor at full throttle rotates exactly 5,000 revolutions per minute. Find the angular speed of the propeller in radians per second. Okay, so once again, this is kind of similar where you're going to have to kind of convert things down. So if you look right here, so they want us to figure out the angular speed. So W equals theta divided by time. And so in this case, they tell us 5,000 revolutions per minute, okay? So we're going to multiply that by 2 pi to convert it to radians, okay? So that will change this to 10,000 pi on top. So 10,000, oops, 10,000 pi, okay? And then we're dividing it by time. Well, right now it's 60 minutes, right? 60 minutes. But if we want our answer to be the angular speed per second. So first thing I'm going to have to do here is go ahead and divide by 60 to convert it per minute. And then I'm going to have to divide by 60 again to convert it to per second. Okay, so right now, let's see. We'll go ahead and I can chop that off right there. And then let's see. We could probably reduce that a little bit further. So our final answer is going to be a decimal. So I'm just going to let the calculator do a lot of this for me here. Okay. So let's see. I'm gonna leave the pi there for right now. But let's see what I'm left with. 1,000 divided by 6, and that kind of comes out kind of messy. So let's see. I guess I'll go ahead and convert that to a fraction. So it'd be 500 over 3. So this is going to convert to 500 pi over 3. And now what this is going to be, our angular speed, it's going to be radians per minute, right? It's per minute because I divided by 60. I converted the hour. I converted. Okay, now that I look at this, I think that actually is going to be our answer. I'm sorry, I made a little mistake here on the 60 minutes. So they actually told us 5,000 revolutions per minute. So that was by 60 seconds. And so then once I divided by the 60 seconds, it converted it to radians per second. Okay, so yeah, that's our answer right there. And then if we want to, we can go ahead and put that in the calculator to get our decimal, because that's what they're going to ask. That's what they're going to ask you for on the homework. So we'll go ahead and multiply that by pi, 500 over 3 times pi, and that'll give us 523.6. So 523.6, and that'll be radians per second. Oops. All right. Okay.